Hello again, and welcome back to the second part of this lecture in CT475, where we're doing probabilistic machine learning. So in the first part, we conducted a review of notations of probability and the basics of working with probabilities. So now in this part, we're going to see how we can use that to actually do some classification tasks, machine learning classification tasks. And what we're going to fundamentally work with is Bayes' rule, sometimes known as Bayes' theorem. So, Reverend Thomas Bayes was a mathematician and a Presbyterian minister who lived in London between 1702 and 1761. And he was the first person to introduce a rule for reasoning about what's called inverse probabilities. Now, that is just a special case of what's now known as Bayes' rule or Bayes' theorem, and it was published after his death. Here is a picture of somebody who was, as it's noted there, probably not Thomas Bayes. This is about the only photo illustration, obviously not a photo from the 1700s, the only illustration you'll ever find of Thomas Bayes, but it's disputed as to whether it's him or not, and it probably isn't him. So, leaving that aside, here is Bayes' rule, which is what I showed you at the end of this first half of the lecture. And as I showed you at the end of the previous session, this is easily derived from the product rule. Here is the derivation of it. What we do is, we've got the product rule that says the probability of A and B, the probability of A and B is equal to the probability of A given B multiplied by the probability of B, and because A and B is the same as B and A, it's equal to the probability of B given A multiplied by the probability of A. And we can simply divide across by P of A to get this expression here on the second half. Now these are using lowercase letters here, which means that we're talking about variables or propositions. We're talking about a variable having a specific value. However, it can be equally generalized to variables, not just to propositions. If you remember, a proposition is when you assign a specific value to a variable. But we can talk about variables as a whole and apply Bayes' rule to them. And this is what it looks like. The probability of it looks identical, except now the uppercase notation here means that we're working with variables. Now you might wonder, what is the point of this? Well, the point is that it allows us to reason about some cause that we have not observed. The cause is B, when we have observed its effect. And so this is why we call it inverting probabilities. And it might seem a little strange at first to say, well, if all I want to do is to compute the probability of B given A, why should I need to compute that one figure? I need yet another, a different conditional probability and two absolute probabilities. So I need three numbers just to compute one. Surely I should just evaluate this first one directly. But we'll get back to why this matters. But first let's take a look at the use of Bayes' rule and the implications of Bayes' rule. Before that though, let me talk a little bit about cows and sharks. One of the benefits of probabilistic reasoning and Bayes' rule is that it helps us to deal rationally with estimating risk. Humans are actually not that great at estimating risk. People tend to focus on low probability but high visibility threats. So, sharks. We're all afraid of sharks. None of us are afraid of these cute little cows. However, I've dug into the data, and about one person per year in the USA gets killed by sharks. And according to data that I got from the Center for Disease Control, about 20 people per year in the USA, in the same territory then, are killed by cattle. So That, I guess, means that cattle are 20 times more dangerous than sharks. So that's a concern, isn't it? And I mean, I suppose that raises questions I have to ask myself. Am I an irrational person? Because I think I'm rational. I think I understand probabilities. Yet I will quite happily let my kids go into a field, even if there are 3 or 4 cows nearby. And I won't happily let my kids go into the ocean if there are 3 or 4 sharks nearby. Even though I know that cows kill 20 times as many people as sharks. So, what do you think yourself? I know we're not in a classroom where you can answer back to me, but what do you think is the reason for this kind of anomaly here? That we're more afraid of sharks and yet cows do more killing. Well, we can actually analyze this by picking apart the probabilities. And here we go. Here's a nice probability formula. What this says is that the probability of death being caused by a cow is equal to the probability the cow causes the death multiplied by the probability of there being a cow, encountering a cow, I suppose, and divided by the probability of death. So this is Bayes' rule right here. But it's Bayes' rule applied to this situation where I am trying to understand the probability of death given a cow, and so on. So, and that's equal to the probability of the cow given death, causing death, multiplied by the probability of the cow, divided by the probability of death. Also, small bit of bad news for you in case you weren't already aware of it. The probability of death is 1. So, if you didn't know that, you are going to die someday. I'm sorry to have broken that to you in these circumstances. So, that's the probability of death being caused by a cow. Here we have equally, the probability of death being caused by a shark is equal to the probability of the shark causing the death, multiplied by the probability of encountering a shark, dividing by the probability of death, which is 1, and I've taken away the 1 here because there's no point in dividing by 1, it doesn't change our formulas. So, these breakdowns of deaths caused by cows and deaths caused by sharks, when we decompose the probabilities, we, I think, capture the kind of intuition that you probably had, which is that the probability of an individual shark causing a death is fairly high, but the probability of encountering sharks is actually quite low, because people tend to kind of stay away from sharks. Conversely, the probability of some individual cow causing death is low, but the probability of humans in general being near to cows, encountering cows, is very high. Some people, it's their whole job to work with cows. So, on aggregate, because this value here, the probability of encountering a cow, is so large relative to the probability of encountering a shark, it sort of dominates the calculations, and this is why, on aggregate, more deaths are caused by cows than deaths being caused by sharks. Let's think about another problem. This is a sort of puzzle or problem that often appears in studies of probability, and I think it's worth us our while trying to think through it for ourselves. Here is how the puzzle is specified. Some randomly chosen person, is tested for a disease, and we know that the disease affects 1 in 1,000 people. So we know that, and this randomly chosen person tests positive for the disease. We also know that our test is 99% accurate. And so the question is, what do you reckon? Would you say the person probably has the disease or probably does not have the disease? Now, if we were in a classroom, I might ask for a show of hands. And in general, I get a split vote from students. So where do you stand yourself? Well, if you think that they probably don't have the disease, you're right. So let's figure out why that is. Because of you, I'm sure quite a few of you, probably think that, look, if there's a 99% accurate test and the person tests positive, then they must have the disease. So why is this incorrect? Let's figure it out. Well, what we often find to figure this kind of thing out is that it's often easier if we use hard numbers and just think about things in context. We call these natural frequencies. We reason about them in this way. So rather than talking about some random person, let's say we did the experiment and we have 100,000 people, and we're going to test a whole damn lot of them. Now we know that the disease affects 1 in 1,000 people. So of our 100,000, 100 of them will have the disease, and therefore 99,900 will not have the disease. So far, so good. Of those 100 people, we're going to apply the test. Remember, the test is 99% accurate. So, of these 100 people, 99% of them will be correctly diagnosed as having the disease. And 1 person will be incorrectly diagnosed as not having the disease. This one here is called a true positive. This here is called a false, no, a true, yeah, false positive. No, excuse me. This here, if the person has the disease and it gives the correct answer, then it must say they don't have the disease. So it gave a negative answer. That's a false negative. So we think we're doing okay, and we can understand all of that, but here's what people tend to forget about. If we were assuming we were testing everyone, we obviously cannot test only those people who actually have the disease, because we don't know in advance whether people have the disease or not. So we cannot possibly do that experiment where we only test those who have it. So we're actually going to be testing everybody. And, you know, if we were repeating this experiment on randomly selecting a person 100,000 times, we would be testing everybody. So let's see what happens to those, of those 99,900 people who do not have the disease. Again, we've got this test, 99% accurate. We can run the sums in it, and we'll see that if this test is 99% accurate, it will correctly say that 98,901 people do not have the disease, and that's a correct answer. However, it will also say that another 999 people will test positive. That's 1% of our sample here. Look, that's 1%. 999% of them, or 999 will test positive even though they don't have the disease. So that's another false result, like this false result here. But as you can see, this false result, this false positive, where these people are testing positive and they're wrong, the test is wrong, greatly outweighs the true positives that we had up at the top. And that is why that when we say that of the people who test positive for the disease, they're actually going to be, look, we can sum them up, these people plus these people, that gives us 1,098 people who test positive. But only 99 of them actually have the disease. Therefore, the probability of having the disease, given that this test is positive, and given everything else we know, is 9%. Not great at all. So, therefore, even though the test is 99% accurate, because it's such a rare test, the probability of having the disease, given that you tested positive, is only 9%. Therefore, you know, at this stage, however, you have some evidence that there's something more to look into, and you maybe do more tests and all those kind of things. We'll discuss that later too. Incidentally, it is worth noting before I leave this slide that there have been many research studies using tests like this with various professionals. And all of these studies have concluded that people such as doctors and lawyers and economists and other professionals who should be quite numerous and need to make important decisions, a about 50% to 90%, depending on the circumstances, depending on the ways questions are phrased, is the error rate made by professionals in dealing with questions like the one we've gone through here. So if you were one of the people who would have said the wrong answer on this, you're in good company, I suppose. Let's drill down a little further into this work and work with a more specific example. And this is kind of related to the last one, but we'll work out the numbers on this now. And rather than using this natural frequencies, let's actually work on the formula. So for this example, I want you to imagine that you're a doctor who wishes to assess the probability that a patient has the flu, or influenza if we want to be fancy about it. And all we have at the moment is the knowledge that this person has a sore throat. So the person is called into my clinic with a sore throat. That's all I know about them. The flu at the moment is an unobserved cause. Remember that Bayes' rule is useful for reasoning about unobserved causes when you have an observed effect. So the observed effect is the flu. There is a sore throat, excuse me. The unobserved cause of that might be the flu. The only way to really detect the flu is to draw bloods, I believe, and run cultures and all sorts of complicated things. And it takes time. So if we're just going to do a simple examination, we won't have time to do that. So we want to figure out, in Michael's doctor's surgery, my part-time job is running a doctor's surgery. I want to figure out, is this sore throat caused by the flu or not? So the probability of a sore throat, given that you have the flu, is 75%. So as is written here, my experience based on my patients who show up at my blacklisted clinic in the computer science department, is my experience is that there's a 75% chance of somebody who I know to have the flu having a sore throat. We also know that in general at this time of year there's a 10% chance of somebody showing up with a sore throat. 1 in 10 people have a sore throat. I also happen to know that the flu is fairly prevalent at the moment, and 1 in 50 of my patients have the flu. So from all of that, I can compute the probability of having the flu, given that you've got a sore throat, is 0.75 multiplied by 0.02 divided by 0.01, and it works out at 15%. Based on this evidence and based on this data, there's a 15% chance that if this patient has a sore throat, it is caused by the flu, and therefore I suppose an 85% chance that there are many other explanations for this patient's sore throat. And that sort of stands to reason from the numbers I have here, because I've already said that 10% of my patients show up with a sore throat, but only 1 in 50 of my patients have the flu. So therefore, there are a lot of people showing up who have sore throats and do not have the flu. So that's why the probability, when we run the numbers of the flu, given that you've got a sore throat, is only 15%. So a nice thing that you'll see from this example is that reasoning on the basis of this evidence makes our hypothesis more likely or less likely, rather than simply accepting the hypothesis or rejecting the hypothesis. So that's a kind of a nice thing. You know, when we were using things like decision trees, they just give us a classification. They can answer yes or no. With probabilistic reasoning, rather than doing that, we can say, well, this is now more likely or this is less likely. We can quantify exactly how likely it is, so we can do interesting things like that. Moving on then, we can see, having looked there at Bayes' rule, we can delve into some of the details of it. And we look at, in particular, something called Bayes' rule with normalisation. So that's an alternative formulation of Bayes' rule, which avoids us needing to know the prior probability of our evidence. Remember, in this case, in the flu example, the evidence that the person presents with is their sore throat. So instead, effectively what we're doing is we're going to try and avoid having to know the value of one of our variables by computing some other things and normalizing away. So strictly speaking, what we're doing is we're computing the posterior probability for each value of the query variable, and then we're normalizing. So what we're saying is, if we take a look at these formulas here, the probability of the flu given the sore throat is the probability of sore throat given flu multiplied by the probability of flu divided by the probability of sore throat. That's what happens if you assume that's testing the probability that you do have the flu, given that you've got sore throat. We can also compute the probability that you don't have the flu, given that you've got sore throat, which looks very similar, the formula there. Note now that in both of these, probability of sore throat shows up. So we can rearrange the equations to normalize them. So first, let's make a couple of observations. The first and most important observation is that the probability of flu giving some evidence and the probability of not flu given the same evidence must sum to 1. This is our total probability theorem showing up again. And as I mentioned on the previous slide, we're dividing by the same term the probability of sore throat, so we can eliminate it by normalizing. Normalizing probability of flu given sore throat and whatever other evidence, and the probability of not flu given the same evidence. Also, we should note the probability, the absolute probability or prior probability of not having the flu is just 1 minus the probability that you do have the flu. So let's take those observations and apply them to the example, and here's how we'll do it. What we'll do is we will use this term alpha to denote what we're calling a normalization constant. It's in place of the sore throat, the probability of sore throat we're dividing by. Instead we will multiply by alpha. So, probability of flu given sore throat is alpha times all of this expression. The probability of not flu given sore throat is alpha times a similar expression with not flu fitted in. We already know that the probability of sore throat is, given that you've got flu, is 75%. And we already know that the probability of flu is 0.02. So let's see what we know. We want to compute this and we want to compute that. We've got probability of sore throat given flu, so we've got that, we can use it. We've got the probability of flu, so we can use that. We can say the probability of not flu is 1 minus the probability of flu, which is 98%. So we've got that. The one term we're missing is this one here, the probability of sore throat given that you don't have the flu. So in this case, we need to know the probability of sore throat given that you don't have the flu. And I happen to have that data from my observations in my blacklisted surgery. This is 8.7%. And we can then calculate. We can run all the numbers, run all the formulas, and then if we end up with alpha terms showing up, well, we can just normalize these numbers to get rid of the alphas, because we know that ultimately this probability and that probability have to sum to 1. So alpha times that plus alpha times that have to sum to 1. So we can just add them up and add these two numbers up and divide by them, and then we get these. Probability of flu given sore throat is 15%. The probability of not having the flu given that you've got a sore throat is 85%. And these numbers agree with what we saw before. And here, for completeness, at the bottom of the slide, let me just give you the general form of Bayes' rule with normalization. And it's that as written down here, where alpha is a constant to make the probability of y given x entries sum to 1. Okay, so that's Bayes' rule with normalization, and we've already seen the Bayes' rule without normalization. Let me pause there for a little bit of discussion about Bayes' rule itself. So specifically, what I want to discuss is a question that I raised a few slides back. Why am I going through computing 3 or 4 different variables when all I want to know is the probability of flu given that you've got a sore throat? Well, and after all, I have to have these measured quantities. 3 or 4 times now I've said from experience of my surgery, so I've got raw data that I've computed and calculated to come up with observational data that I've drawn my probabilities from. So if I have all this observational data in my surgery, surely I can just measure the probability of flu given that you've got sore throat directly. And I can. This is called a diagnostic probability. It's a term we use for the probability of a disease given some symptom of the disease. And we could assess it from the observations, as I did with some other values. However, there is a rationale for why we're not going to do that. And that is that causal probabilities are more robust. Causal probabilities being the probability of sore throat given that you flu. So in other words, the probability that your sore throat is caused by your flu. Those kind of causal probabilities are more robust than the diagnostic probabilities, the probability of diagnosing flu from sore throat. And the reason for that is that flu and many diseases can change their frequency from time to time. We well know that flu is a seasonal disease. It crops up mainly at winter time. So if there's a flu outbreak, the probability of flu will increase. And if that happens, we would have to go and somehow reassess this diagnostic probability, the probability of flu given sore throat. And that's going to be difficult to do, because if the frequency of flu has changed, any counts I made from before the outbreak of flu will not be applicable anymore, because they're going to be affected by the relative frequency. If there's a flu outbreak, I'm getting more patients coming into my surgery with flu as opposed to with other diseases. So I can't really use the counts from my outbreak validly. However, I can fairly quickly get data about the overall probability of flu, whether from my own patients or from other reports. And the most important thing is that the probability of sore throat given that you've got a flu is unchanged. Flus give you a sore throat with a certain frequency, and we're assuming here that the flu itself is not a different disease with different symptoms. So it's just the frequency with which flu occurring is different. So from that, if we can appreciate this very important point here, that since the probability that you've got a sore throat given that you've got the flu, in other words, the probability of your flu causing a sore throat for you, is not affected by the outbreak frequency of the flu, because it just depends on the nature of the disease. This means that these numbers here are robust to changes in the frequency of occurrence of the disease itself, and as long as we can remeasure the outbreak of flu, we're not going to be too badly off. Okay, let's move on to the next thing we can do with Bayes' rule, which is combining evidence. So this goes back to the conditional independence formula that we saw when we were doing the first part of this topic. So let's continue with my questionable surgery. And we've already got this patient, the probability of a patient having the flu given that they've got sore throat. But let's also take their temperature and see, do they have a fever? What is the effect of that on our reasoning? So in this case, what we're asking is, what is the probability of flu given that somebody has a sore throat and has a fever? And again, using Bayes' rule, that's proportional to the probability of sore throat and fever given that you've got flu, so inverting the probability, multiplied by the probability of flu. Well, here we run into a problem. We've got this thing here, this probability of sore throat and fever given flu. how are we going to come up with the combined probability of sore throat and fever given the flu? This is called a joint probability. And I spoke about joint probability tables earlier, and we know that they kind of grow large very quickly. So to address this, we will make an observation, and the observation we will make is that sore throats are, we will say, conditionally independent of your fever given the flu. We spoke about conditional independence before. What does that mean? Well, in this case what it means is, sure, if you have a flu, this can result in you having a sore throat, and it can result in you having a fever, but the sore throat and the fever are themselves not inextricably linked. It's the sore throat, they're two independent symptoms of the flu. So they are symptoms of the flu, they're not utterly independent of each other, but they are conditionally independent, given that if you know somebody has the flu or if you know they don't have the flu, that gives you information about them having a sore throat, and it gives you information about them having a fever, and you don't need to reason about the combined effects of sore throat and fever together. What that means is that we can now break out the conditional independence formula that we saw back in the first set of slides, and here it is again. Probability of A and B given X is equal to the probability of A given X multiplied by the probability of B given X. So this is really good, and this might not seem like a major change, but what this means is that for this expression over here, we don't actually ever need to come up with the combined probability of sore throats and fever given flu. All we need to know is the probability of a sore throat when you have the flu, and separately the probability of a fever when you have the flu, not the joint probability of sore throats and fevers given flu. And so, using that reasoning, we can modify the formula as above, and we get this here, that the probability of flu, given that you've got a sore throat and fever, if the sore throat and the fever are conditionally independent of each other, is proportional to the probability of sore throat given flu multiplied by the probability of fever given flu multiplied by the probability of the flu itself. And you can see well, I think that formula now has a sort of a nice symmetry to it. And this step here of observing or deciding that two variables are conditionally independent of each other, this really important step here, this step is really important, because if this were not the case, if these things were dependent upon each other, then we would have to, our joint probability table would increase, the number of calculations would increase proportionally 2 to the power of n. So that gets very intractable very quickly. On the other hand, if all of these evidence variables are conditionally independent, as these two are, then the number of calculations we have to do here just increases linearly with the number of variables we have. So we can move then from having to worry about an exponential problem to a linear problem, which is always great news if we remember these kinds of ideas from when you studied complexity of algorithms. So what this means is that this allows conditional independent statements. These are conditional, allow us to apply probabilistic reasoning to large domains where we might have lots of variables. So that's a big thing. It's good from a big data point of view. Secondly, it's generally much easier to quantify the probabilities of one thing at a time, of the probability of sore throat given a flu, and then separately measure the probability of the temperature or fever given the flu, than it is to try and come up with these paired or multiple variables all together. This whole thing, this whole idea of conditional independence is the basis of the naive Bayes classifier that we are going to examine soon. But first, before we examine the naive Bayes classifier, I want to talk about one more thing, which is called Bayesian updating. And the point I want to make here is that Bayes' rule can be applied iteratively if we want to do sequential testing. So we saw this really with the flu example. Initially, all we knew is the prior probability of flu, that 1 in 50 people have the flu or something like that. Then we checked to see whether our patient had a sore throat, and from that we could compute the probability of flu given that you've got sore throat by applying Bayes' rule to update our knowledge of the flu. Then we can check whether the patient has a fever as well, and we can compute another update, the probability of flu given sore throat and fever, by applying Bayes' rule to the probability of flu, and in fact applying Bayes' rule to the probability of flu given sore throat. And I can't write that, so I'll just skip it there. So a nice thing about this approach is that we can keep applying new independent tests until we reach a probability that's either high enough to accept the person does have the flu, or we get a probability that's low enough that we can reject the idea that they have the flu. And if you want to go back, you can easily check that this iterative idea, if we're assuming that sore throat and fever are independent, that we get exactly the same results as if we take this as our starting point, take this as our starting point and apply that into our Bayes' rule calculations to get an expression for this. So now that we have spent some time understanding Bayes' rule and seeing how we can use Bayes' rule to reason about evidence and unobserved causes, this leads us very naturally to considering the naive Bayes classifier. A naive Bayes classifier is the simplest form of Bayesian classifier. It's sometimes even called the simple Bayes classifier, sometimes just called the Bayes classifier, although that is not a great name because there are many types of Bayesian classifier. This diagram here shows what this diagram on the right here shows what the naive Bayes classifier looks like. We've got one node for every variable in our world, everything that we know about in our world, and the node at the top of this little tree here is our class node. So it is influencing everything else, and it is influencing all of these other nodes, which are the evidence nodes. So x1, x2, x3, x4, these are all evidence of the class that we are trying to make a decision about, and we don't directly observe the class, we're trying to infer what the class is. So an alternative way of looking at it is that C is our root cause, and all of these others are the effects. Either way, whether we class them as classes and evidence or causes and effects, we have the same structure, and we have an arc from the one class node to every evidence node. And note that we have no arcs in between the evidence nodes. They are conditionally independent, if you remember that that's what those diagrams mean from our previous slides. So this is in fact the core of why this very useful classifier is stuck with the name naive. Its naive assumption is that it assumes that all of our evidence nodes are all conditionally independent of each other given the class node. And the reason we call it the naive assumption is that we don't make, or the naive Bayes classifier is it makes this assumption always, even if we know that that assumption is actually true and we're kind of violating it. But we go with it anyway because it just simplifies our calculations. So sometimes we will work with variables where we know there are interdependencies between these evidence nodes, but if we're using naive Bayes, we just have to pretend they don't exist. So, for the little diagram, for that Bayesian network, that naive Bayes classifier that I drew a minute ago, for each arc in it, going from a class node down to a variable x1, we need to have on that arc, we need to annotate it with a set of probabilities. And here is what the probabilities are. The probability of x1 being true, given that the class is true, and the probability of x1 being true given the class is false. Also, we'll need to know the probability of x1 being false given the class is true, and the probability of x1 being false given that the class is false. But we don't need to calculate those two directly, because we know that these probabilities have to sum up to 1. So we can just, if we know the first half of them, we can derive the second half of them. So, if I've got my structure, my naive Bayes structure, and I come up with a set of probabilities, and we'll show you how to do that on the next slide, and then I want to classify a new instance, well, all I am going to do is calculate the probability of each possible class value given the values of all the other attributes. So what this is the Bayes rule with normalization, assuming conditional independence. And what we say here is the probability that class 1 has some value, and class 1 has some value, and x2 has some value, and all the way up to our evidence variable xn, the probability of that joint set, that atomic statement here, is equal to the probability of class 1 multiplied by the product of all of these, the probability of x1 given class 1, the probability of x2 given class 1, the probability of x3 given class 1, and so on. I'm sure you're already familiar with it, but just in case you are not, this thing here, the large pi, is our product. So you're probably familiar with the sigma, the summation. Pi is very similar in notation to sigma, except whereas sigma sums up all of the arguments here, pi multiplies, gets the product of all the arguments. So what we're getting here is the combined probability of all of these values here, and then we normalize those and we select the largest value. Say that's the one we're going to go with. Is we're going to go with the class that is the most probable class. So we'll compute the probability of this class given all of these things that we know about. So this is the only thing we don't know about, so we'll try all the different values of C1, C2, whatever many values we have in our class node, given all of these other things that we do know the values of, and we'll compute their joint probabilities, and we'll normalize those probabilities and pick whichever one is the biggest. Now, you might be surprised to see this that we're writing all of these probabilities in terms of a whole set of conjunctions here, but that's equivalent to, and that's what the note down at the bottom is, the probability of a class given x1 and x2 and x3 all the way up to n is equal to the probability of all those in conjunction multiplied by the probability of just x1, x2, x3 all the way up to xn. And if we before we do our normalization, this has got a fixed value because we've got the fixed set of observations that we're trying to determine the class from. So these won't affect our normalization, so we can throw them away. So it's a constant times that. So therefore, the probability of the joint set of values in this constructing in this atomic proposition is directly proportional to the probability of the conditional that I have here, the conditional probability of the class given all of the evidence that we can see for it. Anyway, don't worry too much about that little technical detail. What's important is that we're doing this calculation here. And I think, let me just back up a few slides. So if we take a look at that, I think we will see that that is actually very much like what we saw in the flu example. So when we were doing this general form of the Bayes rule with normalization, we had the probability of y given x is the probability of x given y by the probability of y with a normalization constant. And when we did the combining evidence, this. We have the probability of sore throat given flu by the probability of fever given flu by the probability of flu itself. Or alternatively, we could write that as the probability of flu multiplied by the product of all the various evidence variables given flu. And you can see that this diagram here that I drew at the time when I was explaining it is the same diagram that we now have for our naive Bayes classifier. And you should again see by examining these things that this expression here is a specific form of the formula that I have here highlighted in the box. Okay then, so in terms of learning with naive Bayes, what do we have to do to train, to construct a naive Bayes classifier, to learn a naive Bayes classifier? It's actually, there's very little required to it. We don't have to learn as such the structure of the naive Bayes classifier, all of these arcs and nodes, because that's fixed. As long as we know what we're trying to classify, and as long as we know what our independent variables are, that gives us our structure. And as for the arcs, well, we just estimate those arcs, their probabilities on them. We have to put a probability in each one of these arcs, but we estimate them from the training data. And we'd call the probabilities for one arc a conditional distribution. So what we need to come up with for a single arc is the probability, if we've got class C and we've got an independent variable x1 that can take on some values, we need to have a set of probabilities there, which is the probability of x having the value x1 given that our class node has a value c1, for example. And to compute that, we just look at our data and see, well, how often do we have class c1 in our set of training data? And of those data, how often are those places where class is c1, how often are those, how many of those does x have the value x1? And that ratio there will give us the probability on this arc. So they're called simple frequency estimates. It's just a very simple counting exercise. And we'll work through a worked example in a few minutes just to make this a little clearer. One thing I'll mention before we go working on a specific example is there's an idea called Laplacian smoothing, which is that what we will discover soon is that in these counts you might often find situations that in your training data all possible combinations of variables that you want just don't actually occur. So if that's the case, if you get a 0 for n1 n of x1 c1, if you get a 0 there, then you get a 0 probability here. And remember, when we calculate our probabilities, we're going to multiply out a whole string of probabilities. If we do a whole load of multiplications and one of those answers is 0, we're going to get 0 for the whole multiplication. So 0 probabilities end up propagating and kind of messing up our calculations. So there's an idea called Laplacian smoothing, which effectively is to pretend that you've observed everything once. And you add some observations. K equal to 1 is a kind of classic case. When I say I've seen everything once, that means K equals 1. You add some extra observations to your data. The motivation for doing this is that by adding these, you'll just make sure that you'll never have 0 probabilities, but these extra virtual observations will always be at smaller fractional values than your true observations. So they're not going to swamp your calculates, but it'll apply some minimum probability to all possible calculations, all possible combinations of your data based on how many possible combinations there are. Okay. Right now, you might find that a little hard to follow. We will work through an example of Laplacian smoothing later, and I hope that when we do that, it will become a little clearer. But first, let's see how we will actually train a naive Bayes classifier. And to do that, we're going to go back to our old friend, the tennis example that we've used in multiple cases. So, first thing we need to do is to come up with the structure of the classifier. Nothing to it. The structure of the classifier cannot be changed. If we are trying to determine whether we're going to play tennis and our independent variables are outlook, temperature, humidity and wind, then that implies always this is the structure of our naive Bayes classifier that we're going to do with it. So all we need to do is to estimate the probabilities on each one of these 4 arcs here. And we're going to not use any Laplace smoothing, we're going to use simple frequency estimates for that. So, we'll begin by considering this arc over here, where we've got play tennis and the dependency between play tennis and the wind. So we want to compute how often does it happen that you play tennis when it is windy or you play tennis when it is not windy. So what we can see from the slide here is that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 cases where we play tennis. Of those 9, 3 of the 9, it is windy. So what we'll say is the probability of wind being true, given that play is yes, is 3 out of 9, or 1/3. Equally, the probability that wind is false, given that play is yes, is all these ones here. 1, 2, 3, 4, 5, 6. So the probability wind is false, given that play is yes, is 6 over 9. And obviously we're reassured to see that those numbers sum to 1, as they should. Now, what about, that's the probability of when we do play tennis. What about the probability when we don't play tennis? Well, we can see there are 1, 2, 3, 4, 5 times when we don't play tennis. Of those 5, 3 of them, it is windy. So the probability of when wind is true, that we do not play tennis is 3/5, and the probability when wind is false, that we do not play tennis, is 2/5. And again, they sum to 1. So that's how we did it for that attribute. We then need to repeat this for the other attributes. So if we do that, we can look at the probability of outlook, play given play, and we can compute all of the values here. You can go and check them for yourself. We can do the probability of temperature given play, and these are the values I've come up with here. Again, check them for yourself. And the probability of humidity being high or humidity being normal given play. So, having done all of that, having done all of these simple frequency estimates, we have come up with, that's all we need for our Bayesian classifier, except for one last thing, which is the overall probability with which I will play tennis or not. And the overall probability of which I'll play tennis is 9 times out of 14. So, the general probability, if you look back at that table, 9 times out of 14 I play tennis, 5 times out of 14 I don't play tennis. So they are our prior probabilities. All of the others are the conditional probabilities on individual arcs. So that set of probabilities plus the structure is our naive Bayes classifier. And with that naive Bayes classifier, we can now ask questions. We can ask, for example, will I play tennis if it's sunny, cool, humidity is high, and wind is true? So what we want to do is, will I play tennis? And the answer is always going to be yes or no. So we will evaluate, we will see what does it work out if I assume the answer is yes. What will work out if I assume the answer is no. We don't have to assume any answers for any of our independent variables, we've got all the values for independent variables. So here we have. Here's the joint probability of play is equal to yes and outlook is sunny and temperature is cool, the humidity is high and wind is true. It's just all of those things. The probability of, according to our Bayesian classification rule, the joint probability of all those things is given by this formula here. So you can see, let me just clear the text. It's given by this, because I overlapped a little bit. We've got the prior probability of playing multiplied by the probability of outlook is sunny given that we play, multiply the probability of temperature is cool given that we play, multiply the probability humidity is high given that we play, and the probability that wind is true given that we play. We go back to the previous values of the slides, pull all those numbers, and we get a final value of a 1 over 189 for non-normalized probability that play is yes. Repeat that whole step for play is no. And this time we get a non-normalized probability of 18 over 875. So now we simply need to normalize these two values so that they sum up to 1. Remember, there's an alpha factor here, I haven't even written it down. If we normalize, what we get is that the probability that play is yes is 20%, 20.5%. The probability of play is no, given all the observations and data we have, is 79.5%. Therefore, our conclusion is we are not likely to play tennis today. So that, I think, is a nice worked example of naive Bayes, and I think if you were to look back at, we've looked at very similar data sets for decision trees and for k-nearest neighbours in the past, and you can see how we may get the same answers with naive Bayes, or we may get different answers. We also, more importantly, get a different type of an answer. We get a probabilistic answer as opposed to a crisp yes or no answer. And from the probability, we are going to apply a threshold in order to reach our conclusion. So, I'm going to look at one more example before we leave it. And the first thing I suppose we should mention that the naive Bayes classifier works well as long as, even though sometimes the conditional independence assumption is not always appropriate. Now, if it's not appropriate, that can mess up the probabilities we get. But, as long as it doesn't affect them too badly, if all we're going to do is compute two probabilities and pick the bigger one, it doesn't really matter too much if those probabilities are very accurately estimated, as long as they're roughly of the right order of magnitude, which is the most important thing. Like that the larger probability is larger, the smaller probability is smaller. However, there are more advanced Bayesian classifiers that we will touch on, not today, but at a later stage. Before moving on, I want to look at one more interesting example of Bayesian reasoning and Bayesian classifiers. And that's one of the spam filters. Spam filters in email. Bayesian naive Bayes emerged as a very good way in the past 10 years or so of dealing with spam messages. And I'm going to take a look at an example here. It's not quite spam email, but we get spam in a lot of different areas. And so if you want to read on screen, we can see an example from a past exam paper of CT475 where I asked students to automatically identify posting to some photo service, looking at the caption text to see are they spam or are they legitimate. So here I've got some very normal looking spam type messages saying talk about weight drugs and drug news and click this link. And here are my real photos, which are all things got to do with like puppies and nice things like that. So I'm asked to, using a naive Bayes classifier, compute the probability that two messages, see what the probabilities of them being spam are. Weight drug news and puppy news. Now you might look at these and say, okay, that is, the one talking about drugs looks like spam, the one talking about puppies looks good. And I hope that will turn out when we run the numbers on these, because we have to show all the steps in our computation and explain our assumptions. So, formally then, what we're talking about is that this is our training data for our naive Bayes classifier. And we are then going to, having trained our naive Bayes classifier, we're going to apply it to these two new queries and try to get some results. When we go to work with these kind of text processing examples, very commonly we use what's called a bag of words representation. You might have come across this in lectures on information retrieval. A bag of words representation means that we don't actually care about the sequencing and about the ordering of words. It's as if we just throw all the words into a big box and have them all lying there. We're not going to worry about the semantics of the words. We're not going to worry about the sequencing or the ordering or which is a verb and which is an adverb, any of that parsing. We're just going to treat the existence of a word as a feature. Now we might do some small tidying up. We'll obviously, forget about uppercase versus lowercase. We might get rid of plurals and we might do some other simple tidying up. But we just treat the words as whether or not there's a word present, that's a yes or a no. That's a feature in our representation. Okay, so how could we use a naive Bayes to tackle this problem of spam? Well, let's look at the set of messages we had first. The spam messages here and the non-spam messages here. And these are our training data. And as we can see, we've got, each message has got some words in it, obviously. So we're going to look, sometimes we're going to look at the level of how many messages we have, and then we're more often going to look at the number of words we have. And we see there are some words that overlap. The word news shows up in both sets. So then we cannot just check, and then the word drug, for example, might show up if you, in some situations in non-spam. So we can't just base our decisions purely on a simple word. But we want to base them on the evidence of the combinations of words together and the frequencies of those words. That's going to be our evidence in filtering for spam. So, overall, first, in our naive Bayes classifier, we've got to have the probability of spam is determined by our features, and our features are our words, word 1, word 2, word 3. So what is the overall probability of spam? Well, in this training data set here, we have 7 messages in total in our tiny little training set. Obviously not realistic, but just so we can do it by hand. And of those messages, 3 of them are spam. So from this data, without using any Laplacian smoothing or anything, we can say that 3 out of 7 of our messages are spam, and 4 out of 7 are non-spam. I think it's estimated at the moment that some shocking amount of email, maybe 90+% of all email is spam. But most of it never gets through to us because modern spam filters that are built on Bayesian reasoning, Bayesian classification, are very good. So okay then, so that's the overall probability of spam, that's the overall probability of non-spam. What about the probability of the word news, given that it's a spam message? Well, here are the spam messages. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 words in our collection of spam, and of those words, news occurs once. So we're not counting unique words, we're counting the occurrences of words. So 1 out of 9 of our, it's very messy, excuse me. 1 out of 9 of our spam words is the word news. For the word news in non-spam, well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 non-spam words, and again, one of them is the word news. So for non-spam, it's 1 out of 11. It's the probability of seeing the word news in this training set of non-spam. Right then. So here's a slightly improved version of that diagram I scratched on the previous page. For a message M is a collection of words. This is our bag of words representation. We want to compute the probability of spam given the set of words in this message. And we'll do it just like we did for the tennis example. We will try non-normalized. We will say, well, what's the probability of spam given this collection of words? What's the probability of non-spam, or ham as it's sometimes called, given this collection of words? And using Bayes' rule and the naive Bayes assumption, the probability of spam given this collection of words is first, it's the prior probability of spam multiplied by the probability of word 1 in spam, by the probability of word 2 in spam, by the probability of word 3 in spam, and so on. So we do that, the non-normalized probability for spam, the non-normalized probability for non-spam, and we normalize those two values. And we're going to take a look at two examples here. One is for when we get a new message saying puppy news, and we get another new message saying weight drug news. And we're going to compute them without using any smoothing first, and then secondly, we're going to do them addressing the question here, how do we change these calculations if we use Laplacian smoothing? So what I'm going to do now is I'm going to switch over to Microsoft Excel, and we will take a look at these figures inside of Excel. So now, I have opened my spreadsheet with the naive Bayes calculations for the case that we were looking at. Let's pop over and remind ourselves this is the Bayesian spam filter, and this was the data set that we had with click this link, weight drugs link, drug news here as the spam, puppy sleeping today, good luck puppy, good sleeping and new meeting today as our non-spam. So here, I have over on one side, I've written down all of the words that I see, and I've counted up for these words, how often they occur in the spam group and how often they occur in the not spam group. And some words like news occur in both groups. So that's our set of different words, and you can check for yourself. There are a total of 13 different words here. So we're going to first tackle the question of, if I get a message saying puppy news, is that message spam? It doesn't sound like spam to me, so let's see if that's, given the focus of our little example, so let's see if that's true or not. Well, first, what's the prior probability of spam? Well, it's 3 over 7, as we decided already. What's the prior probability of non-spam? It's 4 over 7. Oh, so that number there, 0.571, if you look up in the formula bar up at the top, 0.571 is 4 over 7. Our overall formula is the probability of spam given a message is first the prior probability of spam by the probability of word 1 given spam by the probability of word 2 given spam, and so on. So we need to come up with the probabilities of all those words given spam. So word 1 here is puppy. So what's the probability of that word in our spam set? Well, here's our spam set over here, and puppy does not occur at all. So in fact, using simple frequency counts, the probability of that word, of the word puppy in spam, is 0. What about the probability of that word in the non-spam section? Well, here's our non-spam section, and puppy appears 2 times in those 11 words. So the probability is 2 over 11, which is 0.1818. What about the word news? Well, the probability of that word in spam, we already figured this out, I think. Here's our spam set. There have been a total of 9 words in our spam set, and one of those occurrences is the word news, so that's 1 over 9. Likewise, the probability of that word in the non-spam set is 1 over 11. And that's the last word we have. So, we can now compute, and there's in the formula bar again, the probability, the overall probability of spam given this message is a prior probability of spam plus the probability of word 1 given spam plus, or multiplied by the probability of word 2 given spam. Multiply all those out, and you get this value here, which is 0 because of the 0 that showed up in our calculations. Whereas the unnormalized probability of not spam given that message is this number here, 0.009445. We want to normalize those, so we sum them up and divide by the sum, and this is what we get when we normalize the text that's highlighted at the bottom. We get that the probability of spam given this message is 0, the probability of non-spam given this message is 100. So sure enough, in our photo application, something with the subject puppy news, we rate it to be completely, definitely not spam. Now we're very definite about that, and that's a bit unfortunate. We don't like to be quite so absolutist because we don't know everything. And the reason we're so definite is because this word does not occur, the word puppy does not occur in our spam set. We've got no evidence of it, and that makes us very certain. But we should be careful about being making overly strong statements, particularly because of absence of evidence. So that's why we want to introduce the Laplacian smoothing. We'll see that in a couple of minutes. First, here's our calculations for the second sentence, weight drug news, which to me looks a lot like the sort of spam group of messages we had. Let's see if that's borne out by the calculations. First, prior probability spam, the prior probability non-spam are unchanged from before. Our first word is weight here. What's the probability of the word weight given spam? Well, 9 spam words, of those weight occurs once, so it's 1 over 9. What about in the non-spam? Well, here's our non-spam, and the word weight doesn't occur at all, so that's 0 out of 11. Drugs occurs 2 times out of 9 in the spam, and 0 times out of 11 in the non-spam. And news occurs again 1 time out of 9 in spam and 1 time out of 11 in the non-spam. So we compute the products of the prior probability plus each of the conditional probabilities. And for the probability of spam given that message, we get this number here, 0.001176. But for the probability of non-spam, we get 0 because, again, we've got some 0 observations, 0 probabilities in our evidential data. And so even when we do the normalization, 0 stays at 0. And our final conclusion is that for this message here, weight drug news, that there's 100% chance it is spam, 0% chance that it is not spam. And again, as I said, we don't like to be overly confident, particularly based on absence of data. And since we have a very small training set, these zeros will occur, and even in large training sets, zeros can occur, and they are to be avoided in probabilistic calculations. So let's introduce the Laplacian smoothing. Let's try and remember first what Laplacian smoothing was about. Well, Laplacian smoothing, I'll run back and find the slide where I introduced the idea. Sorry now. In Laplacian smoothing, we want to avoid 0 probabilities, and we effectively add extra counts. So when we're getting a ratio, as we were doing here, of the number of occurrences, say, of the word drugs in the spam set divided by the total number of spam words, we'll add an extra set of observations. We'll add 1, and then also the total number of observations we have. So let's see that in practice. Here, the prior probability of spam is, we will pretend at the very start we didn't just see 3 spam messages and 4 non-spam messages, but we will introduce 2 more virtual observations, one that is spam and one that is not spam. So that means that our 7 messages goes up to 9 effectively, and instead of having 3 out of 7 as we had before, the probability of spam is now 4 out of 9. The probability of non-spam is 5 out of 9 instead of 4 out of 7. So we've added an extra virtual observation there, and you can see it's slightly changed the probabilities, not by a huge amount. 0.428 became 0.444. 0.57 pulled down to around 0.55. For our first word, because we're going to apply this to class smoothing on the query of weight drug news, for the first word weight, the probability of the word weight given spam, we're going to modify that now. Well, again, we're going to assume that we've seen every single word once. If we've seen every single word once, there are 13 possible words, and we will have seen weight once in an actual observation and once in a virtual observation. So instead of having 1 over 9, it'll be 2 over 9 plus 13, as shown there. Likewise, for the probability of this word weight given non-spam, we'll add an extra observation there. Then, for the probability of the word drugs, instead of having 2, we will have 3 now, and we'll have total number of spam observations is 13, because we'll assume that every single word appeared at least once in the spam list, and every single word appeared once in the non-spam list. So here, we're going to add the 13 observations, so instead of having 2 over 9, we've got 3 over 9 plus 13. And here, instead of having 0 out of 11, we've got 1 out of 11 plus 13. Likewise, we modify news in the same way, and we now calculate our overall unnormalized probability of spam given the message, which is this number, and the overall non-normalized probability is not spam given the message, which is this number here. We sum them up and normalize, and finally we end up with this conclusion here, which is now, using Laplace smoothing, the probability of spam given the message is no longer 100%, it's still high, it's 86%. And the probability of not spam given the message is no longer 0, it's still a low number, it's 13.8%. But fundamentally, we have avoided the zeros. And effectively, one thing you can think of, one of the effects of Laplace smoothing is it sort of reweights our probabilities to bring them always, all of the probabilities move a little bit towards 0.5, which is, you know, if you think of it's something that's true or false, 0.5 is sitting on the fence. So you move things a little bit away from the extreme views and move them towards the sitting on the fence. So you can see 0.4 prior probability of spam increased a little, 0.57 prior probability of non-spam decreased a little. They both moved in the direction of 1. They all move away from 100s and all move away from zeros. And you effectively are beginning by saying, look, every possible word might have at some stage appeared in a valid message, every possible word might have at some stage appeared in a spam message, and then starting from that assumption, we will look at the recurrence of the words to estimate, as we have done in these calculations here. Okay, so that's the worked example of the spam and Bayesian spam filter. And having run through all of that, we are now finished for today. So we've seen how the naive Bayes works, and we've seen how the Bayesian spam filter works. And we've also even seen how the calculations change if you use Laplacian smoothing. Now we're going to finish the lecture here for today. Next week we will conclude a part 3 of this topic, which will be focused on Bayesian networks. Bayesian networks are a more elaborate type of structure related to these naive Bayes structures that we've seen here. So next week we will build on our new understanding of probability and our new knowledge of the naive Bayes classifier and see how we can extend those ideas a lot further. Bayesian networks are very interesting. Not only can they be used for tasks such as classification, we can do a lot more with them, including representing knowledge and exploring the relationship between different variables in a domain. So, I look forward to working through that topic with you next week. Thank you for your time and attention. We'll see you then. Goodbye.